Okay, so welcome everyone to the virtual workshop, Introduction to Spatial Capture-Recapture. My name's Andy Royle. I'm a researcher here at Patuxent Wildlife Research Center. I have just a very brief overview here of the next 3 days, and then I'm going to go into an introductory lecture on basic concepts of capture-recapture. We'll also do a round of introductions of the 4 hosts here. We're not going to do a whole workshop-wide set of introductions that we would normally do in a longer in-person workshop, but we know a little bit about everyone from the Slack introductions. So thanks for doing that. If you haven't done it, add something about yourself to that Slack channel. Okay, so we've been doing these oSCR workshops for a long time. I think the first one was in 2013. They were originally spurred by this Spatial Capture-Recapture book that came out in 2014. Although since then, they've taken on more of a likelihood-based framework, driven mainly by the development of this oSCR package, which has been something that Chris has really taken the lead on. And we've done a series of workshops at Smithsonian and other places that really focus on maybe a more accessible, user-friendly oSCR workshop. And you guys are getting the really brief version of that workshop here today. There are some resources for oSCR help and the oSCR package help. I listed those forum links at the bottom of this slide. So hopefully you can go there and seek help for any problems or questions that you have. And also related to the workshop, there is the Slack channel that you can ask questions on as we go and even after the fact. So the shorter version of the workshop, this is going to be three-day event with about 3 hours of lectures and discussion each day. Today, day 1, I'm going to give an introductory lecture covering basics of capture-recapture and then concepts of spatial capture-recapture. And then Chris will give a lecture on fitting basic oSCR models in the oSCR package. Tomorrow, we're going to talk about really essential classes of models for people who are doing capture-recapture studies, multi-session models, models for modeling spatial variation and density, and then day 3, integrating telemetry and resource selection ideas into oSCR models, and then design of oSCR studies, which is a really, really important topic that a lot of times doesn't get enough attention at the initial phases of a real field study. So that's an overview of this short online webinar style of workshop. With that, I think we'll go around and the hosts can all take a half a minute or so to introduce themselves. I've introduced myself already, so let's go with Chris next.
Hi, everybody. So I'm Chris Sutherland. I just started a new position in the University of St Andrews in Scotland, my homeland, a month ago. I'm still trying to get there though, so that's a bit of a problem. Yeah, as Andy said, I've been doing a lot of work kind of creating this package. Really, it started when I was a postdoc with Andy and Angela Fuller at Cornell, where we were just kind of tried to fit models that that really weren't available to us yet in any standard software package. So that's how the package came about. But I'm an ecologist by training, and kind of towards the end of my PhD, I decided to venture into the quantitative dark side, and I spent a lot of time there really for my career since. So I describe myself as a quantitative or statistical ecologist, and I'm excited to be here talking to you all. It's nice to have so many people here willing to learn this stuff.
Okay, how about Dan?
Hi, everyone. I'm Dan Linden. I'm a statistician at NOAA Fisheries. I worked with Andy and Angela as a postdoc at Cornell like Chris, and that's where I met Chris also, and started contributing to oSCR for some work that I was doing, and haven't stopped. So looking forward to meeting new folks and talking about some concepts in spatial capture recapture.
All right, Gates.
All right, hey everyone. Hope you can see me here. My name is Gates DuPont. I'm a master's student in Chris Sutherland's lab at UMass Amherst before he heads over to Scotland. Working on optimal sampling design for oSCR and general like a statistical ecology focus. But yeah, excited to be here and excited to give the design lecture on day 3.
All right, thanks everyone. So with that, I'm going to move into this introductory lecture. I'm going to cover basically two topics here. I want to give some background on capture recapture ideas, so basic non-spatial models. So things I'm sure if everyone in this workshop has been exposed to these ideas, but the idea is just to kind of calibrate everyone and then build some basic concepts that we extend as we get into spatial capture recapture. My second objective is to introduce everyone to the essential ideas of spatial capture recapture. So capture recapture is a class of models for estimating population size and other demographic parameters from what we call individual encounter history data. A fairly broad class of useful capture recapture models are closed population capture recapture models, where the basic idea is that repeated sampling of these populations take place over a period in which there's no change in population size. So there's no operative dynamics like recruitment, mortality, immigration, and emigration. If that's the case, we call these populations closed. That's the closure assumption. So under repeated sampling of these closed populations, we capture individuals, we mark them, and hopefully we recapture some of them. And from that sequence of captures and recaptures, we're able to estimate certain population parameters and dynamic parameters, as well as parameters that describe how individuals are captured. In the old days, capture-recapture studies almost always involved physical capture and physical marking of individuals, so ear tags, color bands, and so on and so forth. But nowadays, more and more, studies don't use physical capture at all, but rather devices like camera traps or non-invasive genetic sampling, where we can record an encounter of an individual without actually seeing it or getting our hands on it. So as I said, capture-recapture models use individual encounter history data. Encounter histories are just a record of when an individual is captured or not. It's usually organized in a two-dimensional array or a table, like I show here, where a 1 in this table indicates that an individual was captured. A 0 indicates that the individual was not captured. So individual 1, the first row of this table, was captured in sample occasion 1, sample occasion 3, and sample occasion K. It wasn't captured in sample occasion 2. So that's a basic individual encounter history, just a sequence of zeros and ones indicating when individuals were captured or not captured. When we conduct a capture-recapture study over K sample periods, we wind up with a data set on a set of lowercase n encountered individuals. So that's the data set that we would normally analyze. And kind of a key feature of capture-recapture is we wind up with some number of individuals in the population that don't produce any encounters at all. So in the bottom of this table, we show in red here individuals, lowercase n plus 1, n plus 2, all the way up to uppercase n here. Those are individuals that exist in the population but don't produce any encounters. And in a sense, the inference objective of all closed population capture-recapture models is to estimate how many of these all zero rows there are in this hypothetical data set. So those are individual encounter histories. That's kind of a key feature, this fact that big N is unknown. We want to estimate how many of those zero encounter histories there are. An interesting thing about this data structure is there's no spatial information at all here. So this table has is structured as individuals by sample occasions, but there's no way to deduce anything about the spatial structure of the sampling. But when we do real capture-recapture studies, these zeros and ones almost always originate from some kind of spatial array of traps or some kind of spatial sampling structure like transects or track lines or something. And none of that spatial information exists in this classical capture-recapture data structure. And so really what we hope to do with spatial capture-recapture models is acknowledge that spatial structure and then build models that integrate that spatial structure. Now, the model structure for basic closed population capture-recapture models is very simple. The typical assumption is that these individual encounter events are just Bernoulli trials, a little mathematical expression in the middle of the page here. We say that the encounter of individual I and sample occasion k, that's y with a subscript ik, is a Bernoulli trial with a parameter p also indexed potentially by individuals and sample occasions. And that's the parameter that we call detection probability or encounter probability in a capture-recapture model. In a sense, what this model says is that individuals in a population on the landscape are just flipping coins to determine whether or not they appear in your capture-recapture data set. So this is just a really simple coin flipping model that describes the encounter of individuals in a population. It's exceptionally easy to simulate individual encounter history data. There's just a few lines of R code at the bottom of this page that you should be able to clip out of the PDF document. You should be able to just highlight those, cut them, and then paste them into an R console. It should execute and give you, if you set this value of this parameter P, the number of sample occasions, you can use the R binom function to just simulate an encounter history for some individual in a population. So it's really, I think, important to be able to understand models by simulation. And if you're doing a thesis project or even a real field study, at some point you're going to want to be simulating hypothetical populations to understand maybe aspects of sampling design or model performance or something like that. Under this binomial sampling model, you can compute this quantity that we call P star, which is the probability of capturing an individual during a given study having K sample periods. And this is just a quantity that is determined completely from the binomial sampling model along with independence of sample occasions. And so P star here is a quantity of some importance. It's the probability of being encountered during the study. And the reason this is important is because under the binomial sampling model, you can relate the number of captured individuals, that's lowercase n, to the population size of individuals, that's this uppercase n, through this P star parameter. In fact, the number of individuals we capture is also a binomial random variable. And from this simple expression, again, induced by the binomial sampling, we can develop or describe what people often call the heuristic estimator of population size, by just taking the expected value of little n and then rearranging that to get an expression for big N. That's shown at the bottom of the page here. I don't know if people can see my pointer, but this is the heuristic estimator of population size. And it just really, what this does is it just makes it clear how estimation of population size requires knowledge about detection probability. All of the detection probability parameters are balled up in this, this P star quantity. And this just makes clear that we have to know something about that to get an estimate of population size. So building models for detection probability P is a central focus of capture-recapture models. There's this classical monograph by Dave Otis et al. 1978, which provides a catalog of all kinds of different closed population capture-recapture models that vary in how different variables affect detection probability. So I'm going to give a real concise overview of these models here momentarily. They're listed at the bottom: model M0, model MT. They have this kind of nomenclature that is widely used in the literature. And so for sure, if you've been involved with a capture-recapture study before, even if you don't know this monograph, you know this nomenclature that people use to describe capture-recapture models. One kind of really useful way to think about capture-recapture is that all of these standard models are really just variations of logistic regression models. So we have this Bernoulli model, this coin flipping model for how we encounter individuals. And all of these classical models, M0, MT, MB, and so on and so forth, really just differ in how structure is imposed on that parameter P that varies by individual and sample occasion. So we're all familiar with logistic regression, I'm sure. We build models on the logit scale of a probability parameter P. So if we have a time variable in this logistic regression model, that's essentially what people call model MT. We could put an indicator of whether an individual was previously captured. That's a model MB, the behavioral response model. We could include even random effects. So we have a parameter epsilon here, which maybe that has some probability distribution to describe variation among individuals. That's a model for individual heterogeneity and detection probability. So there's all kinds of different covariate structures that you can impose in this basic capture-recapture model. And I'm going to go through a little bit of a description of each of those. So model M0, the null model, is the simplest possible model that essentially assumes that there are no covariate effects in the model for P. So in other words, detection probability P is constant for all individuals in all occasions. It does not have a subscript I and K. It's just one parameter. And so in terms of this logistic regression model, we can express it as a logit of detection probability is just some constant beta naught. Models of time specificity are really important. So model MT assumes that this detection probability parameter P varies by sampling occasion. And there's variations of this sort of time specificity. We could assume this is a really common model that's used classically, is that at each sample occasion, has its own detection probability. So P depends on K, and on the logit scale, it's just some coefficient beta with a K subscript. So this is used when, when there's a small number of sample occasions, like a weekly sampling occasion, monthly sampling occasion, or whatever. It might make sense to have K such parameters. If you're doing a camera trapping study or something like that, where there's maybe a nightly sampling interval, that's a lot of parameters, and so you might want to consider more parsimonious models. So we could have P that varies as a function of time-varying covariates. Like, for example, it could vary smoothly over a sample season, or it could vary in response to environmental attributes like weather. And so we could model, build a kind of a classical looking logistic regression model relating those P parameters to covariates. And so there's a lot of variations on these models for time specificity that we could consider. So the next model I want to talk about is, I think, one of the more important classes of models in a lot of capture-recapture studies, and that's a model MB, where the detection probability parameter P depends on whether an individual was previously captured. And this is an important model because it accommodates either trap happiness or trap shyness in studies. So if you're using baited traps and you're capturing small mammals, they might respond positively to having this bait, and they might be more likely to be captured subsequent to their initial capture. Similarly, if you're capturing individuals and it's they require a lot of handling and it's traumatic, they might be very averse to being captured subsequent to their first capture. And these kinds of processes can be modeled as a behavioral response, which again looks just like a logistic regression model. Another important class of models is model MH, which are, the H stands for heterogeneity. These are models for individual heterogeneity in which detection probability varies by individual. So you can think of this as every individual in the population has its own detection probability, so that some individuals are captured with a higher probability and some are captured with a lower probability. And the way this model is usually formulated is that we think of P, we put an I subscript on P, we think of that as a random effect. So we have to specify some probability distribution for this parameter P sub I. So for example, at the bottom of this slide, we could assume a model in which on the logit scale, detection probability has a normal distribution with some mean and some standard deviation. Another type of model is what people call a finite mixture model, which is really just a discrete distribution for detection probability. You could imagine a population has two values, individuals in a population have two values of detection probability. Some individuals have a high value, some individuals have a low value, and that describes your population structure. So for example, if you can't tell males and females in a population, you might imagine that this kind of structure is due to that sex structure in the population and the fact that you're not able to observe it. So the reason that this model MH is so important is because in real studies, unaccounted for heterogeneity among individuals leads to bias in estimating population size n. So if there is heterogeneity in P in the population, what you tend to observe in your sample are individuals that have higher detection probabilities. And you disproportionately observe those relative to the individuals that have low detection probabilities. And so you're going to wind up with an estimate of P that is too high. And if you think back to that heuristic estimator, you're going to wind up with an estimate of N that is too low. So being able to account for this heterogeneity is really important. And historically, people have used variations of model MH to adjust for heterogeneity and detection probability induced by spatial sampling. So this is, we try to illustrate that concept with this simple plot at the bottom of the page here, where you imagine, let's say, setting up a small mammal grid with an array. It looks like 8 by 8 traps here. So you put 64 traps out in the field to catch meadow voles or something. And depending on where those individuals' home ranges are, some individuals are going to have low detection probabilities. Some individuals are going to have high detection probabilities. So this individual in the lower right here has a home range that encompasses 7 or 9 traps, and you're way more likely to capture that individual than the one on the left here that only has exposure to, let's say, 2 traps. So that concept of induced heterogeneity due to spatial sampling is a really, really important concept. And historically, people did not try to account for that mechanistically, but they tried to account for that, I guess you could say, phenomenologically, using this model MH or variations of the model MH structure. So as I said, there's many types of models for accounting for heterogeneity. The logit normal model is one. You could assume that P has a beta distribution because it is a probability, so that's a natural model for that type of random effect. I think the model that's most widely used in capture-recapture is what people call a finite mixture model. So that's that discrete model that I talked about a couple of slides ago, where you assume that individual detection probabilities can only take on a finite discrete number of values. So there's just a number of latent classes in this population. So again, if you don't measure sex, if it's difficult to determine sex of individuals, then it might be natural to think of a population as having 2 classes with 2 different values of P, and then some proportion parameter psi that allocates individuals to those 2 groups. So this kind of finite mixture model is very commonly used. It's in most software like Program Mark, and also the other spatial capture-recapture package called Seeker. A problem with this finite mixture model is, so people use it widely because it's very flexible. But at the same time, it requires many parameters. You need 1 encounter probability for each class in the population. And then there's also a number of these parameter psi that allocate individuals to classes. So if there's a lot of heterogeneity in the population, it might take many more than 2 classes, and hence almost 2 times C additional parameters to describe that heterogeneity. And there's a lot of work that's been done in the literature on showing a sensitivity or non-robustness of estimates of N to the specific heterogeneity structure used. And so, you know, the point of all of that is really realistic data sets lack information to determine which of these heterogeneity models is the true model, and results are really not robust to the different models. And so that's one reason that I think really motivates the use of spatial capture-recapture models. It's difficult to identify the cause of the heterogeneity in the correct heterogeneity model, but if you believe that it's mainly due to this mechanism of bias induced by spatial sampling or heterogeneity induced by spatial sampling, then you might think to just avoid this heterogeneity modeling altogether and try to tackle the problem of mechanistically modeling the heterogeneity induced by spatial sampling. And when you do that, you arrive naturally at spatial capture-recapture models. I just want to say a brief word on inference and capture-recapture models. In the longer workshop, we have a lot of detail about likelihood estimation, but mainly, if you're a decent R programmer, these closed capture models are sufficiently simple that most people can write the likelihood function out as a block of R code and then just obtain maximum likelihood estimates by using the built-in optimizers of R. More frequently, people use black box programs like Mark, where you just load in your data and you do some pointing and clicking on the class of models that you're interested in fitting. Mark, of course, is probably the most popular thing out there. We also do, in some longer workshops, we talk about Bayesian inference for these types of models. We're not going to talk about it in this short online workshop, but there are, of course, many books now on how to do Bayesian inference in a pretty accessible way using Bugs and JAG software. Okay, the last kind of classical model that I want to talk about, which I haven't talked about yet, is what we're going to call Model MX, or individual covariate models. So the X here is just some covariate X where we think of as being related to detection probability. So again, thinking about capture-recapture as a logistic regression model, we might imagine that there's some value, there's some covariate X that should be in that logistic regression model for detection probability. So encounter probability depends on some measurable covariate. And one of the key technical challenges of these types of individual covariate models is you only know the covariate value for the individuals that you capture. And that requires some gyrations and shenanigans in developing the likelihood inference framework. It's not important here, but that makes the model somewhat more interesting statistically. So what that model looks like is we have our standard binomial encounter model. Again, individuals are just walking around flipping coins to decide if you're going to capture them or not. There's a logistic regression model that relates P to this covariate X. And then in addition, we have some population model for the covariate. So if it's a continuous covariate, we might think that it has a normal distribution, and there's a parameter mu and sigma that we have to estimate. So the big idea behind this model MX, the individual covariate model, is it necessitates some additional model structure that doesn't exist in the other model M0, MT, MB types of models. So one very important type of individual covariate model is sex. So in a lot of populations, it makes sense that males and females have differential probabilities of detection. So that's a great example of a binary individual covariate. It doesn't have a normal distribution because it's binary, but instead it's going to have, again, a Bernoulli distribution. So we could imagine that the population model of sex is Bernoulli with parameter psi, which is the probability in the population that an individual is a male or a female. Of course, the sex ratio then is just going to be psi over 1 minus psi. In most real capture-recapture studies, we're not going to be able to, well, we don't observe sex on individuals we don't capture, but in a lot of cases, it winds up being missing data for some individuals in our data set, especially true if we're doing genetic studies where we can't necessarily get sex information on all individuals, especially true in camera trapping studies where you have to have decent photos of individuals to determine sex. And so we have missing data for some of these. That's seamlessly accounted for in this kind of individual covariate model because we have this extra model component that describes variation in that covariate among individuals in the population. So the reason this model MX, this individual covariate, is, I think, really important for understanding spatial capture-recapture is because historically one way people have used model MX is to define an individual covariate that is related to the spatial location of the individual on the landscape. So for example, if you have a trap array in some region of space and you can buffer that trap array, you could define a covariate X, which is the distance to the edge of the trapping array, or you could define a covariate, which is the distance to the centroid of the trapping array. And if you have then a location of capture of an individual, you can define these covariates, and you could imagine it makes total sense that the detection probability should depend on how far an individual is on average from the edge of the trapping array. So an individual, or the centroid. So an individual that on average is captured on the interior of a trapping array should have a high probability of detection, whereas an individual captured on average on the periphery of a trapping array should have a very low detection probability. That's this Boulanger and McClellan paper from 2001 talk about this idea of defining spatially informative individual covariates. So that's why that model is really important. So how that would work, so we haven't talked about the Fort Drum Bear data set. In the longer lecture, we introduced that a little bit, and Chris might do an analysis of the data, but we have this data set that we use, which is a non-invasive genetic study of bears on a military reserve in New York. The trap array is shown in the upper right here. Each of these dots is like a hair snag that gets hair from bears that come to bait. We could buffer this trap array, and we could compute either the distance of an average capture location to the edge or to the centroid, which is shown in the lower right here. These red pluses are average capture locations of individuals that appeared in our data set. And then I've computed the distance to the centroid of the trap array, and this can be used as an individual covariate in model MX. So in the longer workshop, we actually walk through some examples of this, which I think is pretty informative. This is relevant to spatial capture-recapture because in thinking about these individual covariate models, we start to think mechanistically about how space causes heterogeneity and detection probability. And really, in a technical sense, and this is really true, spatial capture-recapture is just a generalization of this idea of modeling heterogeneity as a function of spatial location. So we talk a little bit about that in the book if you're interested, but we're not going to spend time on that today. So I think this is a really interesting and cool model that is in a sense kind of a bridge between old school closed capture-recapture models and spatial capture-recapture models. So I want to close this this first part of my talk by emphasizing some limitations of capture-recapture. I mean, everybody knows about these models. They're still the most widely used class of models in ecology, I think, but they have some real limitations. And one of those is that they give you an estimate of population size, they don't give you an estimate of population density. And so when you put a bunch of traps out on a landscape, you have to start thinking about, well, what's the area that I'm sampling from this array? You need to be able to quantify that area in order to get an estimate of density. And there's really not a unique way to define that sample area without thinking about spatially explicit models for the encounter process. And so historically, there's just many, many papers that give a whole bunch of various ad hoc solutions to computing density. And there's really no data, and they give you different answers of density. but there's no data-based way to choose among those different ad hoc solutions. The other thing that's a real limitation of classical capture-recapture models is the point I made really early on in terms of the data structure. There's no spatial information in the data structure, so you have no ability to model spatial effects. So for example, if you have a bunch of traps out on the landscape, some might be baited, some might not be baited. They might be different types of traps. They might be out there for a variable amount of time or variable times of the season, and all of these things should affect the trap level probability of detection, and there's no basis at all for accounting for those things in the classical capture-recapture framework. At the same time, there's also, density is a spatially explicit population parameter. It varies for any population. It varies over the landscape as a function of all kinds of things like habitat and landscape structure. And there's no sense in which density is an explicit parameter of classical capture-recapture models. And so this really fundamental ecological question simply can't be addressed by this class of models that doesn't deal with space. The final point is that these models are not mechanistic models. There's no, in addition to density, there's a lot of other spatial ecological considerations that affect individuals on the landscape and how they encounter traps. And none of this spatial ecology can be accommodated in closed population capture-recapture models. So as I said here, capture-recapture models apply to goldfish in a bowl where there's really no interesting or useful structure or words in a book, but maybe not to ocelots on a landscape. So those limitations motivate the need for spatial capture-recapture models. And so we're going to define spatial capture-recapture as the extension of capture-recapture models to accommodate space. Capture-recapture involves a spatial model for how individuals are distributed on the landscape or where they live. And it also involves a spatially explicit capture model that accounts for the locations of the traps. As I said earlier, or I kind of alluded to this, it can be thought of as a natural extension of these individual covariate models, but one that uses the full spatial encounter history, not only when individuals are captured, but also where those individuals are captured. But like Model MX, it does use a spatially defined individual covariate. It's talked a lot about in the book, not really in this lecture in detail. So there's three really critical or defining elements of a spatial capture-recapture model that are not elements of a classical capture-recapture model. The first of those is that we have a three-dimensional data structure. So like capture-recapture, the encounter data are assumed to be Bernoulli trials or coin flips, but we have these coin flips that exist not only for occasions and individuals, but also for trap locations. So our data structure is individual by trap by occasion. It has this additional subscript J for trap location, and that can affect detection probability. So our parameter P now has this additional subscript. So that's the first component of a spatial capture-recapture model. The second component of a spatial capture-recapture model is an encounter probability model that depends on where individuals live. So we usually express that, again, like a logistic regression model, where the logit of Pijk could be beta naught plus beta 1 times distance, or it could be some other function of distance, like the second example on this slide right here, is just like a half normal probability density. So this is a standard distance sampling type of model, and it makes sense to think about this for SCR as well. So distance between where an individual lives, that's this variable S, and a trap location J should affect the probability that you capture an individual in that trap J. The third component, the third essential component of spatial capture-recapture is then a model that describes how individual locations are distributed on a landscape. So we think about one of the aspects of the individual covariate models, model MX, is that the individual location is assumed to be an observed variable. It's actually defined by like the capsule location of the individual. But in SCR, we think of these individual locations as unobserved or latent variables. And so we don't observe these S's for individuals that we capture. We treat them as latent variables, and so we have to impose a prior distribution on those latent variables. And so a really simple type of prior distribution for a coordinate in two-dimensional space would be to just assume that those things have a uniform distribution in some planar region S that is the vicinity of our space in the vicinity of our trapping array. So those are the three essential elements of a spatial capture-recapture model: more complicated three-dimensional data, a spatially explicit model for how individuals are encountered by traps, and then a model that describes how individuals are distributed on the landscape. I'll say just a little bit more about each of these. So the encounter history, the three-dimensional encounter history structure is then not only a record of when an individual is captured, but also where that individual is captured. So we have a whole bunch of encounter history matrices. We have the usual individual by sample occasion, but we also now have this third dimensional, which is trap location. So any individual can be captured at any time in any trap. So this is that much richer three-dimensional data structure. SCR is the extension of capture-recapture to make use of this richer data structure. So the second essential element of SCR is the spatial encounter probability model. So we think of, for example, a really sensible model is this half-normal kernel. So if you plot that in two-dimensional space with the location of an individual by the red dot on the screen here, you could, it makes a lot of sense that the probability of detecting that individual in a trap should depend on the distance to the trap. So it's more likely to be captured in traps that are nearby let's say, home range center of that individual, and much lower in traps that are distant from that red dot. So this is, I think, a model that we're going to use in some of the examples. It's used pretty commonly in applications of spatial capture-recapture. So one important thing, again, I think I said this, I'm going to emphasize it, is unlike the individual covariate model, this location that describes where an individual lives, this S, is an unknown parameter of the model. You can think of it as a parameter. It's unknown, whereas in the individual covariate models, based on distance to the edge or the distance to the centroid of the trap array, it was something that we would compute. And because of that, we need to describe a model for how these parameters S are distributed on the landscape. And we're going to use the term a point process model to describe the population distribution of these individual variables S. So every individual in the population has a value of this two-dimensional coordinate S. They're point locations, and so the class of statistical models to describe the stochastic structure of these point locations is called a point process model. The most common model that we use in every application is a model of uniformity that assumes that individuals' activity centers are distributed independently of one another and then uniformly in the plane. This is called a homogeneous point process. In addition, if we assume that the population size, the number of points in that plane, is a Poisson random variable, then this model is a Poisson point process. So this uniformity model is illustrated in the left panel here, where we have some region with just a random scattering of points that are literally just random numbers in, I think, from 1 to 10 or 1 to 8 in the x direction and the y direction. We could generalize this model by allowing these points to be distributed proportionally to some habitat covariate. That's illustrated in the right here. This is called an inhomogeneous point process, where individual locations here favor high metric values of this habitat variable. So you see more points in the green parts, and then fewer points in the white to yellow parts. So these are two types of models that we would use to describe the distribution of individuals in the plane, and we're going to show you examples of both of those in this workshop. So SCR models in these three essential elements of spatial capture-recapture, we've introduced three structural parameters that SCR models have. There is a parameter P0, which we're going to call a baseline encounter probability. That's a parameter in the detection probability model. There's a parameter sigma, which is a spatial scale parameter, which describes how rapidly that detection probability declines as a function of distance. And then there's a parameter D, which corresponds to the density or the intensity of this Poisson point process. All of these parameters can vary in an SCR model. D can vary, the density can vary spatially or over time. The parameter sigma can vary by individual or occasion, also time. And the parameter P0 can vary by individual, trap, occasion, and so forth. So all of these sort of fundamental structural parameters can be modeled as functions of covariates. And I think that it's really important to understand a couple of things here. One of them is that the last two parameters, the sigma and the D here, are essentially ecological parameters. So the parameter sigma describes, in a sense, how much space individuals use. And the parameter D, of course, that's a population density parameter. These are ecological parameters, and we need to contrast that with classical capture-recapture models, which don't have three structural parameters. They just have one structural parameter that you can test hypotheses about. That's detection probability, and that's not even an ecological parameter. That's just a nuisance parameter that ecologists really don't have any concern with. Whereas SCR models have what are very clearly two clearly ecological parameters. And this is where you can put various ecological hypotheses into play here. You can test those hypotheses using spatial encounter history data. Okay, so before I wind things down here, I want to talk a little bit more about this third element of SCR, this point process model. The point process model requires that you describe the possible locations of points. So where, what precisely are the locations within a landscape where an individual's home range might be located. This is a quantity we call the state space. More technically, it's the state space of the point process that you're modeling. And as I said before, it's effectively a prior distribution for these individual locations or activity centers. And so we don't just have to define the model, the probability distribution for these point locations. We have to describe the spatial region within which they reside. So this state space is a really important part of the model. In a lot of cases, in some cases, it doesn't matter too much how you define the state space, but in a lot of applications, you really have to think carefully about how that state space is constructed. So in practice, what you'll see is often people just using a regular rectangle that buffers a trap array. That's a fine thing to do if you really don't have specific information about the landscape that might cause you to think otherwise. But in some cases, you might have information that would suggest imposing some restrictions on that quantity, the state space. So here's an example that we've taught in a longer workshop. We do talk a little bit more about this, but this is from a study of wolverines in southeast Alaska. The trap array, camera trapping array, is shown on the left there. Those are the black dots, and so naturally the camera traps are placed in habitat that you would hope a wolverine would use, but there's definitely some areas on this landscape that wolverines would not use. So there's all these sounds and bays here. Wolverines aren't that aquatic, and so they're not going to use that habitat. And when you're thinking then about the third component of the SCR model, the point process model, you might want to exclude some of these huge water areas as candidate locations for an individual's home range center or its location variable. So one way to do that, one way to easily deal with constraints on the state space is to define the state space not to be a continuous region, but to define it by a fine mesh of points. So for example, in my small mammal trapping grid example here, we have an 8x8 array of small mammal traps. The red dots are a population of individual locations, home range centers, and we might just then define a really fine grid, define the state space by a really fine grid of points that encompasses this trap array. And then if we had to impose some constraints on the state space, we might just chop out those points. It's really easy to do that. It's also really easy using this discrete, this mesh of points defining the state space. It's then really easy to do maximum likelihood estimation. So when we define this state space object and we plan to use oSCR to do our analysis, we're going to define it by a fine mesh of points. Okay, so that's really the end of my lecture here. And what we think is really useful for people is to try to understand the data structure a little bit by simulating some data. And everybody should have the PDF here. And these code blocks that are in the PDF, I believe you can just highlight those and you can copy them and you can execute them in your R console. And so I'm just going to kind of walk through and talk about aspects of this simulation. You can execute the code as you go here. So the first thing, the first bit of code here defines the state space of this point process component of the SCR model. We're going to define it just by a rectangle from 0 to 13 in the x direction, 0 to 13 in the y direction. We're then going to set the parameter population size. We're going to set that by just drawing a Poisson random variable that has mean 40. So if we were simulating population sizes over and over again, we're going to get on average 40 individuals, but we're going to get some lower values and some higher values. We might get 35, we might get 32, we might get 46, whatever. On average, the density of this population is going to be 40 over the area of this rectangular state space. 13 times 13 is 169. So where the state space comes into play then is we have to generate a population of these individual location variables S, and we do that then by simulating random uniform numbers between 0 and 13 for the x coordinate and then for the y coordinate, and we put those together, and that produces our population of individual locations S. And then we define our trap locations as coordinates. If we're doing just a small mammal study, it's going to be some, in most cases, a regular grid of live traps or something. And then we can plot this whole system. We can plot the trap locations. We can plot the individual location variables by red dots here. And this is a sampling array with a population of individuals that we're going to subject to sampling. If you execute that code, flip to the next page, we're going to load the oSCR library. We're not going to fit a model with oSCR yet, but there's a couple of utility functions that we're going to use in the oSCR package. One of those is this E2 dist function, just computes Euclidean distance in two-dimensional space. We need to compute the distance between each individual's spatial location and all the trap locations, because we want to define the detection probability of each individual in each trap. So if we compute that distance matrix, we define the parameters P0 and sigma, then we can compute some model for detection probability. That's this line of code right here. This is just that half normal looking kernel function. So if an individual's activity center, its spatial location, has distance 0 from a trap, the detection probability of that individual in that trap is going to be P0. And then that's going to decline as the distance increases. We define how many traps we have. So we defined our trap locations up here. So 64 traps. The number of times we want to subject this population to sampling. We are going to produce a three-dimensional array here that then we can loop over the margins of that array, and we can fill it up with zeros and ones, indicating whether an individual was captured in a trap at an occasion. So if you execute all of this, you're going to populate this three-dimensional array. For every individual and for every trap, it's going to have K encounter events. They're going to be zeros for non-encounters. They're going to be ones for encounters of that individual in that trap. So this is really just, you can see that a basic spatial capture-recapture system is a really simple system. You have to define a landscape in a trap array right here, and then you have to define some parameters of the model, and then using loops in R, you subject these simulated individuals to encounter by traps. And this is really useful stuff. Again, just like like with ordinary capture recapture, really, I think like any model, it's useful, and in fact it's important to be able to simulate data like the data you think you're going to get from your study. You should think before you're deploying camera traps, what are sensible values of P naught and sigma? What's sensible value of population size? What are the expected data from my study? What do I expect to see? And this is how you can do that for the most basic SCR model. So just a couple summary lines of our code here. If you use the table function on this three-dimensional array, you see that in the data that I simulated, I think you'll get slightly different results here. I had 71 captures in my 10-day camera trapping study. If you sum the three-dimensional array over the first margin, so that's this command right here, and then tabulate it, you can see the frequency of captures, or the number of individuals captured 0 to up to 10 times. In this case, there was one individual captured 8 times. There were 3 individuals captured 5 times, so on and so forth, and 14 individuals captured 0 times. So this is the population distribution of the number of captures. And of course, when you do an actual study, you don't observe these zeros here. So what we would want to do if we wanted to analyze this fake data set, which I think we're going to do here in a few minutes, we would want to discard those zeros. So here I subset this three-dimensional encounter history to include just the 21 individuals that were captured. So apparently my value of n up here was 35, although I don't think so I generated a Poisson, but I didn't record what the actual value of n was. Apparently it was 35 because when we throw the 14 zeros out, we have 21 individuals left. So now we have a data set that we can analyze using a spatial capture-recapture model. One thing that you can do, there's a utility function in the oSCR package called spider plot. If you input your three-dimensional data array Y in your trap locations, it will give you a visual depiction of which traps individuals were captured in and where those individuals' average capture location is. So this plot, the interpretation of this is as follows. This individual over here in the left corner was caught in 2 traps, and its average capture location is this red S here. This individual right here looks like it was caught in 1, 2, 3, 4, 5, 6 traps, and its average capture location right in the middle. Not surprisingly. So this individual right here was caught in just 1 trap. This individual was caught in just 1 trap. We showed you how to simulate this three-dimensional data structure. If you do a study, there's no way that you have stored your data as a three-dimensional data structure. You're going to have your data in a spreadsheet. And you want to be able to make a summary like this, but you need the three-dimensional data structure. And we have a utility function in the oSCR package that will take your spreadsheet and will convert it to a three-dimensional array so that you can make this, this kind of summary plot. Okay, so that's a little exercise in simulation, which is really important. You should always be doing a simulation before you conduct an actual study. One of the great things about spatial capture-recapture is because it has these ecological parameters in the model. There's all kinds of ecological theory that we can build into the models, and we're going to talk about most of this stuff well, actually, we're going to talk about the first two things in days 2 and 3 of the workshop here, but you can build models that describe spatial variation in population density. You can build models that account for resource selection. You can build in explicit movement models that describe not only ordinary movement of an individual about its home range, but also things like dispersal and transients. You can also build in explicit notions of landscape connectivity to spatial capture-recapture models. And we talked about a lot of those in this kind of review paper that we wrote a few years ago. You can, I think it was put up in the Slack channel, so you can check it out. We're not going to go into the level of detail we would normally on these things, but it's a lot written on the topics already. Okay, so my summary slide here, a point I made earlier is ordinary capture-recapture models for closed populations are models essentially for fish living in a bowl. And so if you're not studying goldfish, you might think about using spatially explicit models. In studies that we do in practice, the encounter history data that we obtain are really expensive to collect and really valuable for rare species. We should use the full encounter history that we obtain. That includes the spatial information, not just the temporal information. And then the third point is spatial capture-recapture models, because they have these 3 model components, 2 of which are essentially ecological. oSCR facilitates the study of spatial population ecology from individual encounter history data. So if you're interested in questions of ecological theory and process, you can use oSCR as a framework for achieving some of these objectives.